Today, I'm specifically trying to talk about angular momentum conservation. There's three styles of problem having to do with this. The first is the single body problem. It's not necessarily a single object, but it's an object that we treat as a single body. So this problem is a problem, and I'll try and give you a simple definition. So we're talking about a problem where there's no external net torque, but the problem's moment of inertia changes. This is a conservation of momentum question, and I like to call it the single body problem. Not to be confused with a point mass collision. If you recall to the beginning of the semester, we talked about conservation of momentum. There were collisions, one object coming in contact with another. And so all of our conservation of momentum questions dealt with the momentum being transferred from one object to another. So one object slams into another, they stick together. We broke those up into classifications of collisions. A point mass collision with angular momentum isn't any different. It's a collision. Therefore, it's clearly a situation in which momentum may be conserved. But consider like a merry-go-round problem. The point mass collision with angular momentum might be a problem where a kid goes running at a merry-go-round. Linear momentum will not be conserved in this collision because if the kid jumps on the merry-go-round, the linear of momentum of the system will stay zero, right? Because the merry-go-round doesn't suddenly go this way because the kid jumped on it, right? It's fixed to the ground. It's not going to suddenly go across the schoolyard. But if the kid does jump on it, the kid and the system might begin to spin. Well, there's a way to use conservation of angular momentum to deal with this question. And so I call this a point mass collision with angular momentum. And we'll talk about this after the break. Now, the third category is a combination, something where there's both linear and angular momentum conservation. So I'll just write the word combo problem. Today, though, we're going to do the single body problem because it's pretty straightforward. And to do the single body problem, we're going to use a relatively straightforward example that I think almost all of you can kind of imagine. Imagine a schoolyard merry-go-round. I know it's hard because they don't have them in too many schoolyards anymore or playgrounds at all, but do you understand what I mean by a school merry-go-round? A platform that's horizontal on the ground, mounted in such a way that it can spin on its axis through its middle. So we are looking top down on this object. And to give us something to go by, let's say that this object has a radius of 1.5 meters and a mass of 250 kilograms. So it's pretty big, pretty heavy. That's over 500 pounds. And let's have it spin at 1 rotation per second. That's pretty fast, but I just want to use some simple numbers here. Okay? Now, let's populate it with 4 kids. Each kid, 30 kilograms. And let's say that each kid is standing at the edge of the merry-go-round. So each kid is themselves a distance 1.5 meters from the edge of the merry-go-round. Everybody good so far? So these 4 kids all ran around the outside of the merry-go-round and then all jumped on at once. And from that moment, the problem begins. Do me a solid. Calculate the moment of inertia of this system. It's 2 parts, right? Moment of inertia of a disk plus 4 times the moment of inertia of a kid. Pretty straightforward, right? You'll need your calculators. And you got to do all the heavy lifting here. So I'll help you out. The disk is 1/2 m v squared. There are 4 kids, each of mass 30, and they are standing 1.5 meters away from the edge squared. So hurry up, take a moment, calculate the moment of inertia of this system. I am totally calling on people by name, so get busy punching buttons. Because if you say I don't know, you understand what that's going to mean for you, right? Sadness, of course. And if I received a pie today, you should be exceptionally sharp on the calculator. JK, I hold no grudges. Pretty sure I deserved it. We about ready? Nathaniel, can you tell me what the moment of inertia is? What's that? 551? I don't disagree with you. I just want to make sure somebody else got it. Anybody else get 551? Sounds good to me. 551, let's be careful here. Kilograms meters squared is the units for moment of inertia. 551.25? I'm good with 550. I would be okay with 550, to be perfectly honest. So if you have more decimals, good. I'm not writing them. You should be able to tell me the angular momentum then. Right? You have everything you need, but you will have to put this in radians per second. So angular momentum is I times omega, but be careful, you have to have your values in radians in order to get the appropriate units for angular momentum. Hurry, hurry. Multiplying 2 numbers together, radians per second, shouldn't be hard to do here, 1 rotation, 6.28 radians, not hard here. Come on, hurry up, faster, faster. We ready? Donovan, what do you got for angular momentum, please? And that's going to be kilograms meters squared per second. All right, we have established the angular momentum of our system. If no external torque acts on our system, now there probably are external torques, right? Friction in the bearings. These kids aren't going to spin forever. But let's assume that all these kids are on a magical spinning merry-go-round that will spin forever. What happens to the moment of inertia of the system if the kids all walk to the center of the merry-go-round? Does the moment of inertia increase or decrease or stay the same? It's going to decrease. The portion of this that is the disk doesn't change, but suddenly that number changes, doesn't it? Right? Let's say that they walk to a quarter of a meter away. You can't read that because it's too small and too messy. So I'll just write it over here, that they walk a distance of 0.25 meters away from the center of the merry-go-round. So you're calculating a new moment of inertia of the system. The disk part hasn't changed, but the kids have. So I still have 1/2 times 250 times 1.5 squared. But now the 4 kids, still 30 kilograms, are now 0.25 meters away from the edge. So we are changing the moment of inertia of the system. Hurry, hurry, hurry. Be done fast. What do you got, Vicky? Hurry. Once on the hot seat, never relieved. Got 10 minutes, and you know they're going to interrupt us for the alma mater, so we gotta hustle. Come on, Vicky. No pressure. 288.75? All right. I'm going to go 289, but you guys do 288.75 kilograms meters squared. Now, here's what I hope is the obvious. If there is no external torque, the angular momentum before has to be equal to the angular momentum after. This is a conservation of angular momentum problem. I call this a single body problem. What this really means is that the moment of inertia before times the angular speed before has to be equal to the moment of inertia after times the angular speed after. Our moment of inertia got smaller, so I expect this thing to be spinning faster now. Don't you? This is what happens when I pulled my arms in while spinning. I changed my moment of inertia, and therefore my speed increased because the angular momentum had to stay the same. So do it. I want to know, how fast am I spinning now? You've got everything you need to do this real quick. It should not take you long. And you can leave your answer in radians per second. That'll be just fine. We're comparing the 6 radians per second from before with whatever we're going to get now. Hurry. I'm going to call on one of you. Could call any name. Any name. Push those buttons fast. Are we ready? Ty, can you tell me? 11.97 radians per second? Wow. Right, twice as fast. Right, it was 6.28 radians per second before, and now it's almost 12 radians per second now. The kids just walk to the center, and it's going much faster. Now, that part's easy. Everybody understand this part so far? Pretty straightforward? Now, before we go on to the next part, there are a lot of things that you should be able to know, but I understand what it means to be a student and forget things. So consider the fact that there's lots of little questions in here, things you're not thinking about, like the fact that each one of these people has a tangential velocity when they're at the edge, and a smaller tangential velocity when they're in the middle, right? Which suggests to me that they're experiencing one centripetal acceleration when they're out here and a different centripetal acceleration when they're here. And if you're on this ride, you feel as though you're being flung off the ride. In fact, you have to apply a force just to stay on the ride, right? Because you need to have an unbalanced force towards the center. If friction's not enough, you have to hold the railing. That's why there are rails there for you to hold on. Make sense so far? Here's the thing I want you to do, and we're going to split the room up in half so we can get this done before the bell rings. I would like this side of the room to tell me how much kinetic energy we had before the kids walked over to the center. And I want that side of the room to tell me how much kinetic energy the system had after the kids walked to the center. And because I just saw a look of sheer panic on somebody's face, I really should slap them, but it's not hard. We're just talking about 1/2 I omega squared. You guys on the right, you have one set of variables to work from. You guys on the left have another set of variables to work from, and all the numbers are actually right here printed. So you're just punching numbers in your calculator. This is the before, and this is the after. I'm calling on 2 kids. If you're wearing your senior shirt, you can bolt.
Have a good spring break. And seniors.
All right. But if you don't have your senior shirt on, hustle. All right, I'm ready to start calling off people. Are we ready? I'm ready. Let's start with the before kinetic energy, shall we? Emily, what'd you get for before kinetic energy? 10,889? 81? Jules? Is that the right number? Excellent, excellent. And let's see, Zach, give me the after.
I got 20,686.
Okay, is that clear? These are right. Now, listen to what this means, and take notes if necessary. If I asked you how much work was done by the kids, this is how much work was done by the kids. They changed the kinetic energy of the system by walking towards the center. Unlike our other stuff that we've talked about before, energy's not conserved here. The kids did work. They lost energy. And it should be obvious. We clearly see this, right? Although the momentum didn't change. The kids have less energy now because they gave it to this rotating platter. And although they're a part of it, they're traveling slower now, right? They're towards the center. And they don't even have to hold on as much, because there's less force acting on them because they're not having the same kind of centripetal acceleration required. But they did work on the system. Anybody who's been on a spinny ride? Is there anybody who's been on like the hat ride? Or, I'm sorry, the teacup ride or something like it, where you got the thing in the middle that you spin and you'll feel yourself against the edge? Of course, the force you feel is causing your centripetal acceleration. How many of you fools made the mistake of looking up? Any of you? Yeah, I hate it. I hate it for 2 reasons. 1, makes me feel sick a little bit. But 2, have you ever tried to bring your head back up? Is it easy? What do you think you're fighting against? Right? You're doing work. You're having to push yourself forwards. That's what the kids did. When the kids tried to walk to the center, they had to push against their natural desire to be flung off with their inertia. And by doing so, did work on the system. That's why their kinetic energy is greater afterwards. This is a standard single body problem. It's going to involve centripetal motion, conservation of angular momentum, and work done on the system. All right, folks.